Hi, everyone, and welcome to the last quasi-informational cyber seminar in our 2019 National Water Center Summer Institute series. I'm Danielle Tiarina with Quasi, and I am joined today by Dr. Ehab Meselhe, professor at Tulane University, and Dr. Fred Ogden, who is a visiting senior scientist at the National Water Center in Tuscaloosa. And both Fred and Ehab have been involved in the Summer Institute for the past 2 years. And Fred was a theme leader both of those years, and Ehab was a theme leader this last summer. And so this webinar is really intended to give listeners more information on the Summer Institute experience, and specifically from the perspective of the theme leader. And then we'll go ahead and delve into their past Summer Institute involvement and look at some highlights from past projects. So just some housekeeping. We really encourage you all to ask questions, and you may do so at any time in the chat box of the webinar, and then we'll address all of the questions at the end of the talk. And also, if you have any issues during the talk, feel free to chat with the Quasi staff organizer, or you can put your hand up and we will do what we can to help you out. So with that, I'm going to go ahead and pass it on to Ehab, who will be presenting first. All right.
Right, can everybody see my screen clearly?
Yep, we can see it.
Okay, great. So hello everybody. My name is Ehab Meselhe. I had the privilege to be a theme leader last year in the 2018 Summer Institute, and I had the group that you see their picture and names right there, Kelly, Sean, and Miriam. And it really worked very well because they had a different set of skills. Kelly was really good in organization. She had really great organizational skills, documenting and reporting on the work, creating graphics. Sean was very strong in his analytical thinking about the problem and identifying the approach. And Miriam was very strong in writing scripts and codes. So that variation in their background and set of skills helped us to have a very successful research project over the summer. And this is something that always works well, is if people team up with other group members that are somewhat different than their strength, then you end up with a very well-rounded group and you actually learn from one another. So I will go through exactly what we worked on together. From my perspective, we wanted to look at channel routing as a component, an important component of the national water model, and we wanted to explore the possibility of developing an approach to vary the routing scheme in channels so that we can capture strong dynamics or dynamics that are not captured by the current method used in the national water model, which is the Muskingum-Kunj. However, we realized that switching from Muskingum-Kunj to other types of approaches is going to cost computational time. So the idea here was to explore the possibility of developing an approach that can be dynamically implemented so that we don't go to a more computationally expensive method everywhere and all the time. So we wanted to identify when and where would we actually need a higher level of analysis, like a diffusive wave or a dynamic wave. So that was the research question in front of us. So we devised a dynamic wave model or a code that I developed during my PhD research, and we wanted to look into the behavior of the momentum equation and the behavior of the different terms in the momentum equation, and look at when are the different terms become important enough to merit activating a diffusive wave or a dynamic wave. So that's the problem statement that was presented to the students. And I asked them, here is the code. and here is the research question. Let's develop an approach to explore the possibility of devising diffusive and dynamic wave, and when and where do we actually need to activate them. So this is the triangle of the objective that we're calling it. We want to enhance the competition or reduce the computational cost as much as possible. We want to improve the accuracy, and that's the goal that we wanted to accomplish. We wanted to improve the accuracy beyond what the Muskengamkunch can give us, but we didn't want to do that at the expense of substantially increasing the computational cost. And just as importantly, we did not want to interfere with the robustness. Robustness here, we are referring to the ability of the model to run failure-free. Obviously, for an operational model, computational failures are completely unacceptable. So that's the triangle that the students had to keep in mind at all times. How can we increase accuracy without compromising the other two? In front of us in the slide here is the momentum equation. The top form is the dynamic wave, which is all the terms. If you ignore the first two terms, those are the inertia terms. And if you drop the next term, which is the GA dy dx, that is the pressure gradient term, and you end up with the kinematic wave. So these are the three levels that exist in the momentum equation: dynamic, diffusive, and kinematic. Obviously, the kinematic is the most computationally efficient, and then progressively they become expensive as you go up. But also the dynamic wave is the most accurate, and the accuracy deteriorate as you go down. So there is a trade-off between these two, accuracy and computational costs. So this is another way to put the workflow, if you will. The students and I tried to, and Kyle, I apologize, there was a co-theme leader with me, Kyle from Columbia University. So together we wanted to identify when and where do we actually trigger a change from a kinematic wave to a diffusive wave to a dynamic wave. And so we are trying to develop what we call dimensionless scaling parameters. They are triggers. They are flags that if we notice them, then we can code in switches to go from one wave type to another. But how do we actually identify and calculate those dynamic dimensionless scaling parameters, and how we calculate them without actually adding additional layer of computational costs? So these are the challenges that the students were facing to develop something that is actually implementable in an operational code. Ultimately, we wanted to have this diagram here. While you're executing the national water model, you will have the geometry of the channels and you have your initial conditions. We quickly calculate those dimensionless scaling parameter, the DSP. We identify which wave type is appropriate, and we do the triggers and we run the appropriate wave. That is ultimately what we would like to have, and preferably is to minimize the cost at all times, computational cost. So in order for us to get to that level, we wanted to run a dynamic wave model so that we can learn the behavior of the full equation, and run as many scenarios as possible so that we can identify those DSPs and when we can do the switches and where, and start to develop those flags or triggers as we discussed. And that is obviously a pretty challenging task to do. And it's actually quite impressive that during the few weeks of the Summer Institute, they were able to really take tangible steps toward that approach. Obviously, it was not realistic to complete the entire thinking process, but we really took pretty substantial steps during those few weeks. And we identified some regions of where we can actually switch from kinematic to diffusive to inertia, but understandably that we did not explore all the possibilities, so we just identified those as future steps. So a little bit more details of what the students did. They took that channel code that I gave them, which is very simple Fortran code. They started generating scenarios, and I will explain what scenarios did they generate, run them through the Fortran code, and here is what some of the things that they examined. They tried a range of different hydrograph types, different speed of wave moving down the channel. We tried different channel slopes, from very steep to very mild to flat. We tried different roughnesses, so we can see also the impact of roughness. And they also tried a range of downstream water levels, tailwater conditions, basically. We examined all of those in a simple rectangular channel that is 10 kilometers long. And as a subset, we focused on the M1 curve profiles, understanding that there will be a lot more work that needs to be done for all different water surface profiles. And we did not have the opportunity to examine adverse slopes and some other conditions. But at least we focused on the M1 curve to develop the concept and the approach. So the students developed short of just shy of 200 different realization of steady state flows and about 170 or so unsteady flow simulations. For the steady state, we analyzed the final step in every simulation as our source of information. And for the unsteady, we analyzed every time step and every water surface profile there as a single realization. And that actually gave us a very large data set, even though that we were examining only one profile type, but it still ended up being a tremendous data set to analyze. And so we ran all these different experiments through the mesh code, calculated all the flow parameters or all the terms in the momentum equation, and we started the analysis. And we did also, for all those flow conditions, calculate a set of DSPs, and I will share with you what DSPs we actually examined. So those are the set of dimensionless scaling parameters following an older publication, and these were our starting set. This is not the only set that we could examine, but they did cover a good range of the different prevailing governing components of the momentum equation. The Courant, which is give us the speed with the wave is moving, Froude number so that we can capture gravitational forces. We wanted to examine definitely a parameter that reflects the roughness, the slope ratios between the bed slope and the energy or the friction slope, pressure gradient effects, so that will help us to understand when the diffusive wave is important, on a kinematic flow number, and a diffusion number relative to advection. So it's a pretty good set to start with. We actually, at the end of the experiments, we identified that there is some redundancy, so we can reduce those, and maybe there is room to add some more. So basically, we also analyzed those three terms, term number 1 and 2 and 3, which is the inertia term, and the pressure gradient term, and the kinematic term. And then we started to calculate for every water surface profile those different wave terms and compare their relative magnitude to one another, so we can see when each one of those terms dominate the equation. We understand that the three of them combined will always equal to 0, but we wanted to know the relative magnitude for one another. And how does that relative magnitude changes from smooth surfaces or smooth channels to rougher channels? We wanted to examine during an unsteady or a wave propagation down the length of that channel, how do their relative magnitude varies, as you can see in the graphs animated on the left-hand side. And as you can see, it's actually quite complex patterns that will require a lot of thinking of when can we actually switch from one routing scheme to another or routing type to another. So it's not pretty straightforward process, and it will require a lot of thinking, but we put ourselves in good position to actually develop those tools so that we can explore the relative magnitude of these different components. We also started to look at visual way of the relationship between those DSPs and the wave terms so that we can start to develop the triggers. What is the response of the DSPs for those different wave types? So we looked at them in terms of, for the visual analysis, comparing the inertia terms versus the pressure gradient term. Versus those DSPs, and that will let us know what are the regions in time and space where inertia, which means that the dynamic wave is important, or the diffusive wave as represented in the pressure gradient. And then we did also sorting of those DSPs so that we can identify the range, again, in time and space where different wave types are important. So here are some of those visuals that we generated. The three-dimensional graph that is being rotated in front of you is the vertical axis is the Froude number. And then the two horizontal axes, one is capturing the inertia term, and the other one is the pressure gradient term. And the concept here is we're trying to define in that space of all these realizations, where is the region in time and space where the kinematic wave is sufficient for us to use, and when does the diffusive wave become necessary, and when is the dynamic wave becomes necessary. So very preliminary results that can be shown in the graph on the left. When the inertia term is small, and when the pressure gradient term is also small, that is the space where the kinematic wave is important, because the inertia term is not very strong, pressure gradient terms are not very strong, then that's the space where the kinematic is actually sufficient to give us reasonable results. And then how about when the inertia terms are small enough? That is the space where the diffusive wave becomes important. I do not want to use those numbers, the 22% and the 74%, as actually conclusive outcome, but I would say that those are for only the conditions that we examine. This is another way to also look in the space, both the time and the temporal and spatial universe, where are actually the range of applicability of these different wave types. So we took the momentum equation. If we normalize the three terms by the kinematic wave, then you can end up with inertia over kinematic plus pressure gradient over kinematic is equal to -1. So if the pressure gradient over kinematic by itself is equal to -1, for example, then that space, the inertia is equal to 0, which means that we do not need the dynamic wave. Basically, in the two dashed line that you see there, that is where the pressure gradient over the kinematic is in the range of -1. So anything outside that, those are the realizations that indicate that the dynamic wave is not important. So I'm just showing you an example of the level of rigor that these students were able to accomplish in a very short time period. And really, despite the fact that we did not finalize the entire set of possibilities, but they really defined and established a really good approach for us to examine the space for where each wave type is applicable. They definitely learned a great deal about Fortran coding, scripting, and the actual physical interpretation of the different terms in the dynamic wave. So these are all benefits that they walked away with, both understanding of the hydraulic basics and principles, and also coding experiences. This is also additional statistical analysis that we started. We didn't really go too far in that one in terms of identifying relative momentum terms in there, where we calculate the absolute value from all the realizations that we have, calculated the absolute value of the inertia as a term magnitude. And then we also calculated the absolute value of all the sum of the terms, which is basically the absolute value of every individual term. And then we calculated that relative term, which is taking each one of the term by itself, dividing it by the sum, and to calculate basically those different DSPs. So the statistical analysis that we did was not quite conclusive for a couple reasons. One is that because of the redundancies between the DSPs, made the analysis quite difficult. So we probably need to go back and reduce those and eliminate the redundancies, and maybe identify some additional DSPs that will shed some more light that are not overlapping too much with others. And then we can actually carry that analysis forward. But I would like to wrap it up by really summarizing a couple output from that experience. One is that the students really did a great job of learning a bit more about the basic fundamentals of channel routing. They learned a great deal about during that summer institute about coding, scripting, generating graphs, analyzing large data sets. They worked really well together. And I learned a great deal from them as well. So overall, it was a really good experience for the students and for the team leaders themselves. So I will be happy to answer questions either about the technical details or about the experience itself.
Yeah, sure. If anyone has any questions for Ehab, you can go ahead and type them into the chat. And thanks, Ehab, for speaking. I'll go ahead and do the present. And if not, then you can still type the questions in, and then we can answer them all at the end. So, all right, well, with that, I guess we'll go ahead and introduce Fred Ogden. He is at the National Water Center, and we'll be talking about some of the 2019 Summer Institute themes. So, go ahead.
Okay, so thanks, Danielle. Ehab did a really nice job of showcasing the work that was done by the group of students that he was affiliated with this past summer. And I thought last summer I was a co-theme lead with two other faculty on the hyper-resolution modeling theme. And we're not doing that theme this summer, so I thought that I would talk about one of the proposed themes for this summer's activities, which I think is really interesting because it's directed squarely at trying to improve the performance of the National Water Model in terms of its predictions of runoff. So let's go to the next slide. The background that I'd like to kind of start with is this figure, which was produced using data from the USGS Historical Climatological Stream Gauge Network for basins that have, so those basins have minimal human influence in terms of diversions or reservoirs. And those basins that we analyzed also have mean annual precip estimates. So we're able to take, over the period of record, the mean annual runoff and divide it by the mean annual precip to produce an estimate of the mean annual runoff ratio at the continental U.S. scale. And I see this as a really interesting organizational principle to think about the problem of continental scale runoff prediction. So some really interesting organizational features kind of fall out of this data set. Probably the one that you notice first is that the runoff ratios are highest in the Pacific Northwest. And of course, they get a lot of rainfall up there. And usually when it falls, it's in the cold season, so there isn't a lot of ET. so most of it runs off. You see a little bit of that effect in the northeast, but it isn't as strong. The second thing that jumps out at me is the band of really low runoff ratios in the middle of the country, which is over the High Plains Aquifer up into the north central plains down into Texas. And the High Plains Aquifer is the sandy detritus left over from the weathering of the Paleo Rockies. So there's very little runoff produced there. Down into Texas, you get into very complex hydrogeology. You have a lot of losing streams. And up in the northern high plains, you get into the pothole, some of the sink regions. But that's all along about the 100th line of longitude, which is where roughly P is equal to ET. So that's kind of the high plains phenomena there. And then you see Florida has low runoff ratios. That's because almost everything, the rivers are hard to gauge. There's management. There's a lot of groundwater recharge going into the limestone karst system there. There's a big bullseye and precip around the mouth of the Mississippi. You would expect high runoff ratios there, but no. All up the Mississippi Valley, you see intermediate values of runoff ratio because when the rainfall falls, ET is usually high. So there's a lot of ET. You see the rain shadow of the Appalachians. You see in the coastal plain Piedmont of the mid-Atlantic area, modestly low runoff ratios, but over on the upwind side, on the northwest side, you see pretty significant increases. In the Rockies, you see high runoff ratios in the watersheds that have one big runoff event every year associated with the snowmelt dynamics of the Rockies. In the deserts of the Southwest, you see low values except in one basin that happens to have a very strong groundwater component. So that is a very interesting way to look at continental scale hydrology. You can see there's a lot of heterogeneity in process, and that is something that a continental scale hydrology model has to be able to simulate. So we'll keep that figure kind of in mind as a guiding principle. Next slide, please. You look at the runoff processes that are happening, say in the Southwest or the high plains, the semi-arid West. During rainfall, you can have intermittent bursts of runoff that are produced, but they're very transient. Water tables tend to be low, and they tend to result in losing stream reaches in many sites. Whereas when you go into the humid and semi-humid areas, when you have above average rainfall, you can get a persistent high water table that varies seasonally. So in the summer and fall, you'd expect the water table to be a little bit lower than in the spring and winter. You can have active seeps, gaining streams. The processes that lead to runoff generation in those two situations are quite different. So we need a model that can account for both of those runoff end members and the spectrum of things that can fall in between. Next slide. If we look at the National Water Model presently is formulated to use and interact with the National Hydrography Data Set version 2.1. And this is the distribution of the catchment areas or the contributing areas to each reach of the NHD Plus version 2.1 network as in the current operational version of the National Water Model. And one thing that you notice, there are some big ones, but by and large, they are very skewed distribution towards small catchments. You can see that by far the largest single class is catchments that are less than about 0.3 square kilometers, or 30 hectares. And then you've got, looks like the mean is about 2 square kilometers. The median is about 1.36 with a standard deviation of about 2. So it's very much a non-uniform distribution and skewed to the smaller catchment areas. So what it means is that the National Water Model represents millions of small contributing areas. So if we're going to predict runoff, that's the scale that we should focus on. Next. Now this is a look at the NHD Plus version 2.1 network, and these figures were provided by Dave Blodgett of the U.S. Geological Survey, who's working with the Water Center in a collaboration to try to improve our representation. Those very small catchments that arise in the NHD Plus network are the result of very short distances between contributing tributaries to the NHD Plus network. So that top middle figure shows the catchments that are associated with the native version 2.1 NHD Plus network. If you apply different thresholds, so if you snap or spread tributaries that are within some threshold, say if they're less than 2 kilometers, you would split them. If they're greater than if they're greater than 2 kilometers, you would split them. If they're less than 1 kilometer, you'd merge them. You get that network that's in the upper right. If you change that threshold so that you split 3 kilometer reaches or merge 2 kilometer reaches, you get the lower left catchments. And then if you think back to that distribution of catchment sizes, they go all the way out to several hundred square kilometers. If you split those, you can try to impose a more uniform size distribution on the NHD Plus network. And that's an area of active research that we're looking at right now. But the thing is, the NHD Plus network varies regionally depending on who digitized it and how they did it. And in some parts of the country, they're going to extremes in terms of trying to digitize every drainage that you could imagine. So that would be more like a 1 to 1,000 scale, where most of the country is more representative at the NHD Plus of a 1 to 120,000 or 1 to 24,000 scale. Next slide. So if we think about how we can deal with the heterogeneity of process within the National Water Model on a refactored NHD Plus hydrofabric, we start thinking about questions of model appropriateness, which would focus on hydrologic predictability effects, parsimony, verifiable appropriate dynamics, different data sets that we can use to test different model formulations. There's a wide variety of hydroclimatic physiographic or hydroregions, as we could call them, over a range of scales. So that gives a pretty wide range of things that we want to consider. We probably don't want to use the most complicated model that we could imagine. We probably would like to identify the simplest model features that we could that would be most appropriate in different hydro regions. Next slide. The modeling outcomes, and this is what we would hope to achieve at the end of the Summer Institute, would be education of participants in important processes for accurate hydrologic modeling at representative scales that are appropriate for the continental scale simulations that we hope to achieve. Consideration and use of existing hydrologic theory and proven models with physical basis. So we'd like a physically based approach at the end of the day, but that doesn't mean that we have to avoid all conceptualizations. We would like to identify the important watershed properties that help to decide which modeling approach is the most appropriate. We would like to test these new approaches in the National Water Model Framework. So that would be incorporating those into a demo version of the National Water Model and ultimately create new research questions that you could use in to guide your research and research in the broader academic community, which is what we want to foster with community development of the National Water Model. Next slide. The teams consist of 3 to 4 people typically. We have regular meetings with theme leads. Literature review is a very important part of the process, and we don't expect everybody on every team to be an expert in everything. We realize that people will have their own areas where they can contribute. We'd like to identify models, approaches, theory that are applicable. We'd like to identify data sets that we can use to test different modeling approaches in one or more hydro regions. And then there'll be a final report and a presentation at a capstone event, and several of the teams from last summer's Summer Institute are presenting their work at the AGU conference in a couple of weeks. And we also have 2 oral sessions and 2 poster sessions on the work that was done at the Summer Institute last year. So it's a good opportunity for students that are attending to visit with participants from last year, and there will also be participants from last year's. The other themes I should mention for the Summer Institute in this next year are hydroinformatics as it applies to visualization of water model output or outputs of hydrologic predictions at large continental scales, and the coastal coupling. Coastal coupling being how can we simulate through the coastal zone the influence of the intersection, I should say, between inland fluvial flooding and coastal flooding could be from storm surge, hurricanes, or just high tide events. So that's what we mean by teaming, but there's a lot going on. Next slide, please. The prerequisites. Programming experience is nice to have. It's pretty hard for students that don't have programming experience to come up to speed. The good news is if you're interested in participating, there is plenty of time to brush up on your own programming skills before you get here next summer, or take a class in the spring. Knowledge of a structured programming language such as C, C++, Java, Fortran, etc. Experience with scripting, Bash, Python, Perl would be good examples, or experience with mathematical programming environment like MATLAB or R. Having one of those skills is sufficient. You don't have to have more than one. The ability to navigate around a Linux command line shell is useful, but if you have your own programming environment that you like to work in Windows or on a Mac, that's fine as well. And if you have any HPC experience, that is also a plus. And one of the things that we will talk about in the spring after students are selected will be opportunities to gain more experience on any of these topics, and the possibility of trying to get a leg up and maybe identifying with one of the theme areas before you get here and maybe trying to get a head start. We'll talk about those opportunities. Next slide. And that's it. Ehab and I will be happy to entertain any questions that you might have.
All right. Well, thank you, Fred, and thanks, Ehab. And if anybody has any questions, you can go ahead and type them into the chat. Looks like we do have one. So we have Ehab and anybody from Federico. It says, what was the background of the students? How much into hydraulic routing or modeling were they before joining the Summer Institute?
Two of the students were master degree candidates, and one was a PhD candidate. I don't think that any of them had substantial knowledge of hydraulic crowding at all beforehand. So we spent a little bit time together working through the equations and what the meaning of every term. So I had several sessions with them. So you can actually gain a lot of knowledge about topics that you didn't have strong foundations on previously. Like Fred mentioned, that you don't have to have all the skills and knowledge in every component. You just need to have something, whether strong analytical skills or strong programming skills in one language. You don't have to know 10 languages. So they each had some pieces of strength that coming in, and then you actually learn as you interact with the theme leaders and as you interact with the other group members. So do not be intimidated that you or assume that you need to have substantial knowledge coming in. The intent is to actually learn through the process itself. But Fred, maybe you can chime in with your own insights as well.
Well, you definitely identified a key thing, is that you don't have to be an expert in basically anything. You have to be you have to have curiosity and a desire to participate in a team. And with those ingredients, in my experience, the students succeed. It's a really interesting opportunity to learn from some very. Last summer, for instance, we had at times 10 theme co-leads in the room on working on with students on the different themes and answering a very wide variety of questions. It's kind of a deep dive opportunity. We throw the students into the deep end of the pool, but we provide them with ample support and educational opportunities on the spur of the moment. So it's a really excellent educational opportunity in my experience.
Yep, I would definitely agree. As a participant in 2017, I was definitely concerned that I wouldn't have the skills necessary to be successful. But like Fred and Ehab both said, a lot of those things you learn when you get there. And if anything, a lot of times people in your group have complementary skills, so you work together and kind of divvy up tasks in order to get your project done. That's a great question. All right. Well, it doesn't look like we have any other questions. So if you do have one, you can go ahead and still type it into the chat. But we'll just kind of go through the slide now. Our Summer Institute participant applications are now open, and they do close on January 15th. So you can find out more information about the applications, and then also about the Summer Institute and all of the themes that Fred mentioned in his presentation at our website, CUAHSI.org/education/Summer Institute. And you can see, so I did mention this was the third cyber seminar in our series, and so you can visit our website to watch past recorded seminars for this Summer Institute series, and the website is below. And also, of course, stop by our booth at AGU. And as Fred mentioned also, this AGU really is a good place to meet and talk with past participants. I know a lot of the theme leads will be there, present theme leads, past theme leads, and then, of course, come talk to me about any information. Since I was a participant, I kind of know the drill. So with that, Fred or Ehab, do you have anything else? Any last comments or anything?
I just want to say that if anyone has any questions regarding anything that I talked about, feel free to send me an email. My email address is fred.ogden@noaa.gov.
Okay, I'm going to go ahead and actually type that into chat.
Okay. I think
And
Ehab would probably entertain questions also.
Yes, absolutely. Same goes for me, Danielle. If anybody have detailed questions or inquiries, please feel free to send me an email. I'll be happy to help clarify anything. And again, I encourage people to apply. It's a really great program. You can learn a lot, not only technically, but you also can develop connections with future colleagues from other institutions and with the staff at the National Water Center themselves. So you really develop network and relationships that can last for almost your entire professional career. So that's another component that is very helpful for professionals.
Yep, I would definitely agree with that also. Alrighty, well, please get in contact with us if you have any questions, and we hope that you all apply to the Summer Institute, and thank you for participating in this cyber seminar series. All right, well, with that, everyone have a great weekend, and see you at AGU.
Thanks, Danielle.
Bye.